present something connected with symmetries and integrability for non-autonomous dynamical systems. Field theories, from a mathematical point of view, are a dynamical system with an infinite number of degrees of freedom. Because of this set, of this infinite set of generalized coordinates, more problems are put together with the other already existing, connected with the quantization, with the formulation of the theory on superspaces or on Carl spaces. So, because of all these problems, many physicists felt the idea of formulate some other models, some field theories on lower dimensions, or so-called mechanical models of field theories. And there are a lot of examples. I already put on the table here an example, a first example, related to the Young-Mills theory. In the 80s, I think, the Young-Mills theory were transformed in a mechanical model. Mechanical Young-Mills model is called. By a simple change, the Young-Mills field was put in this form, where O is orthogonal matrix, and the new coordinates become the color factors Fi. So the Young-Mills equations comes to, for example, in the case I equal 3, comes to 3 second order differential equation, so a system, and the model could be investigated starting from this dynamical model. Another example is the Hamiltonian model, who could be put in equivalence with by a similar transformation with string theory, more exactly with field theory for 2-4. But even in the case of gravity of black holes, there are studies which use the same method. Even in this morning, Professor Vrnjačka showed me a model, very interesting model, starting from the Ricci flow equation, which can be put in the case of 2 dimension in this form, which again is dynamical systems. V is a function in 2+1 coordinates, and he and his younger colleagues, studied this equation and showed that there are a lot of sectors where the equation could be solved. They found explicit solutions. So the function, the equation is integrable. In fact, the main problem connected with dynamical systems is the integrability of the system of the equation of motions. Of course, it is possible we look for analytical solutions, analytical or numerical solutions. If not, we try to find something to tell us when and in what sector the system could be integrated. There are many methods, and you already know, of course, some of them. For example, our German told us about the Lux method. It's also another method, parallel test, that could be applied. But these methods, first of all, are not very simple to be applied. and secondly, not always give very clear results, presumption concerning the integrability of a model. For example, I heard that in this case, the equation didn't pass the Penner test, despite the fact that they found explicit solutions.
Even the weak Penner.
Weak Penner, yes.
The Heavenly equation, right?
Okay.
Heavenly equation, right? So you wrote that this is in 2 plus 1 is called Heavenly equation.
Yes, it's equations. I told you it's from reticular to dimensional equation. In fact, this is the problem I'd like to present. In fact, there is another approach to the integrability. Namely, we could check if some invariant quantities could be obtained for the system, starting from the symmetries that the system presents. There are many attempts to this problem. Professor Topan said in his speech that it would be very nice to have an algorithm to find invariants. And it's true, there is not such kind of algorithm. But many authors presented, how to say, modus operandi, something like this, which could allow us to find some invariants, and from here the conservation laws and more information on the system. I could mention the papers of Ramani Grammaticos and especially Jarmo Hietarinta in physics reports, exhaustive analyzed the Hamiltonian systems with potential in the form of polynomial, in a polynomial form. Also, I would like to mention other interesting results connected with constrained dynamical systems. Yabuz Nutbu obtained some very interesting results concerning the integrability of some models, for example, Vrnjačka model. But there are models which contain second-class constraints only. Something connected with systems with first-class constraints. Some results were obtained by the group, our group from the University of Craiova, using the BRST techniques. Anyway, I will come back to my presentation. So I intend to follow a line allowing us to obtain some symmetries, some symmetry operators, and then some invariant quantities for differential equations. I'd like to say that for non-autonomous dynamical systems, there are 2 or 3 papers of Strackmeyer and Rieder, one of them published in 2000 in Physics Letters, I think, and the other one in 2002. There are the references here at the end of my presentation. But he obtained some results only in the case of a non-autonomous system with 1 plus 1 dimension. We tried here to extend somehow the study, and I will present here a concrete model, the so-called zonal flows model. It's unfortunately not from field theory, it comes from plasma physics, but anyway, it's an interesting model. with the sign that I have to start the presentation. It's okay. So, this is the structure of my presentation, and I will present some short line concerning the manner in which we can obtain the symmetry operator for a differential equation. It seems that it's not possible. I asked.
You can go ahead. I'll try to find the guy.
Anyway, I think it's not very important. It's not very important. No, it really are very simple calculus, and I think it's very simple for everybody to follow this calculation. It's only, let's say, for the students or something like this. That is important. You know the form, the general form of the symmetry operator is something like this: d to dt, d to dqi, and some functions, c and eta. And when we try to put the invariance condition for a function depending on q and q dot velocities, a first extension of this symmetry operator could be defined. And it had this form. Okay. Also, in the case of expressions of functions or expressions containing second order derivatives, we need a second extension of the symmetry operator. So, in the case when we intend to study the symmetries of second order, here is q2 dot minus plus dv to dqi equals 0. When we intend to study the symmetry of this kind of equations, we need the second extension of the symmetry operator to use. And I presented here the lines followed by the guys from Germany, Strackmeyer and Riedel, I told you. And what they show is that this coefficient c and eta in front of u as coefficient that appear as coefficient of u.
For about half a minute, because the Zoom.
Okay, it's perfect. This is okay. Okay. It's better like this.
One more Zoom. We're not blind, yes. Okay. 1 minute will be out.
I will try to be in time anyway. So let me see where we are at this moment. Yes, so it's the study of the symmetry for a second order equation, these equations. We apply the second extension of the symmetry operator on the equation, and we put this condition. And having in mind the form of the second order equation, this form of the second order, where the operator U is this one, this is U prime, and U is this one. You see, there are these coefficients, C and eta, what have to be determined in order to have the concrete expression of the symmetry operator. And using this technique, we obtain a new equation, equation for eta I and for C, and we can
was on the third page.
Yes, here I have to be. We can use here, I will stay here. At the end, we obtain a form of the two operators, of the symmetry operator. This is the form we have obtained. But here, there are some functions of type, only of type, beta, alpha I, and phi, phi I. They should satisfy some equations that are presented here. The equation 3, 4, and 5. There are the equations that beta is not a very simple equation. You see, it's a third order equation. So, in order to see if the system admits or not a symmetry operator, we have to find solution for beta, alpha, and phi from this system, and to find the potential from the starting equation for which we could have such kind of symmetries, of these symmetries. This is the technique, but we will use not a second order equation. Our system, our concrete system, will be a first order equation of this type. So in our case, we have to solve an equation like this. This will be what we will done for our model. Our model is here. This apparently, not apparently, in reality, it's a fourth order, not a fourth order, sorry, a system, a first order Lagrangian type equation, but with 4 degrees of freedom. We will not be able to solve the system in this form to find symmetries, symmetry operators for the whole system like this. I would like to mention only that in this system, E, the function E of x and y, is some kind of potential with a coefficient f of t, depending on time. In the model I told you, usually this potential is somehow embedded by a Gaussian function, and this f of t is also somehow specified. It's exponential of minus t. Our interest is to solve this equation, this system, and to see for what kind of function f of t we could have some symmetry operators. The system presents some symmetry operators. This is an interesting problem because you understand there are many examples in plasma physics of systems, but they are mainly chaotic systems with chaotic behavior. So to find some symmetries in such kind of system, it will be somehow important for from experimental physicists. We use this form of potential. It's the potential Z used in one of the Z models. A and B are arbitrary constants for the moment, but we choose a simple case, the case with A equal B over 3, when there are some equalities of between the derivative of potential and the system in the Poisson surface of section U equals 0. You see already we diminish somehow the number of degrees of freedom. The system has this form. What follows is the check for the Lie symmetry. The general form of it's like this, and as I told you, we have to use the first extension. The first extension has this form, and we will impose the invariance condition. So U prime applies to each of the three equations, and we'll give three general equations, and from there we will try to find C, eta1, eta2, rho, and also f of t, the function for which the system, our system, could admit, in principle, some symmetry operator. We have some simple computations here. A condition coming from the invariance of the first equation, then another equation imposed, which appear imposing that the second equation has to be invariant, and a similar equation when we ask the invariance for the third equation in the system. At the end, this is important, we obtain some solutions for C, eta, and rho, and an equation for f. The equation for f, it's this equation. This is the conditions that have f of t must fulfill in order to have some symmetries, and in this case the form of the symmetry operator is this form. M, N, and B, here it's a mistake, sorry, B it's an arbitrary constant, it's not B of t, not B of t, it's a constant. So we could have now some partial symmetry operator, and I mentioned here three possibilities. Possibilities that we could obtain giving some particular values for the constants. So, as a conclusion, our system describing the anomalies of the electrostatic field in a tokamak could accept these three types of symmetry operators. And this symmetry operator, for example, is accepted if the coefficient, the time dependence of the coefficient in the potential is of this type, C over T squared. A second symmetry operator could appear for any f constant, so for non-autonomous, for autonomous system, and a third symmetry operator could appear for an arbitrary f of t. So the third symmetry operator is a very large one.
What in the algebra do this U prime generate?
What is the algebra?
Yeah,
No.
these operators should generate some algebra.
I didn't check exactly the algebra between the operators. In fact, there are operators that could be in this condition is one symmetry operator. In another condition, it's another symmetry operator. And so I'm not sure that of course, all three operators could appear, but in different conditions.
I mean, if you take two U's choose for M1 and D1 and M2 and D2 and take the bracket.
Yes,
so
yes,
say
we have
something with the same with some M prime and prime and D prime or something.
Of course, to find the algebra of the system. I didn't check this. In fact, it's a new result we obtained, and I checked only, for example, only the if this symmetry operators could generate some invariant quantities. And for example, the first from the operators, which have this form, could have an operator like this. Of course, there are already the elements of my presentation. Of course, there are a lot of problems which follow from now on. For example, it's not very clear for me yet what are the conservation law generated by this one. If there are some trivial conservation law or not. What I presented is only as an example how we could generate some symmetry operators in the case of a non-autonomous system. And of course, it's very interesting from practical point of view for this system. I read in the condition when a lot of the system has in fact mainly a chaotic behavior. To have such kind of symmetry operators seems to be interesting. These are the references. This is
any questions? Well, I have a good kind of question. Well, when I'm trying to understand the meaning of the conserved quantities we have found, I tried to find the recursion structure.
yes, it's an interesting problem to see if the system admits the Hamiltonian structure, many Hamiltonian structure, or to apply the method of recursion operator. Yes, it's possible.
So you can get all of them if you find one recursion structure.
Yes.
Even through some particular solutions environment with respect to some subgroup of the same.
Yes, this is clear. This is clear.
Okay. Any comments or questions? Well, let's thank the speaker again.